This computer is connected to a chain of WSE converters, and the sound card is a Delta 44. The WSE converters require the lowest sensitivity of the Delta 44. And start Linrad. I log in as an expert. Small fonts, no priority, timer resolution, go for the default, and no auto start, in percent, N, width 100%, height 92%. And go here and save with W. Input and output setup, that's U. And A, the sound card, no port audio, and the Delta 44 multi, that is 1. Need more channels? No. And use the extensible format? Yes. Because that will give me 24-bit rather than 16. Sampling speed 96,000. Number of bits 24. And 4 audio channels because we have 2 radio channels. And the WSE hardware. And B, select the output. No port audio. The SB live, and then D for the parameters of the WSE system. The LPT1 standard is 888, that's the digital, and I have it on pin 11. This may be different in your system, and I don't want to change any crystal corrections. X, and save. Now I can go into the SSB mode, D, and accept all the standards, except this one, toggle mode, that is C. I want manual mode now when I'm experimenting and demonstrating things. Here. There is now no input signal, and I set the frequency 10.7 megahertz and switch on a signal here. The amplitude of the signal gives a headroom to saturation that I find by press A. There's 40 decibels, so I need nearly 40 decibels more signal, or 40. The signal is now minus 50 dBm, so I change it to minus 10 dBm. And the margin is now a fraction of a dB. I change the display a little bit so we see better. Signal, mirror, and harmonics. Second harmonic, third harmonic, fourth harmonic. Now that the signal level is right, I can calibrate the balance between I and Q to get rid of the mirror image. That's X. Then A for balancing of amplitude and phase between EI and Q. Here you can see the signal and the mirror. They are both very close to the end of one of these 32 regions. It's better to have them a little bit closer. Maybe something like that. The algorithm has to be able to separate this one from that one, which certainly wouldn't be any problem with these positions. But it's also good to have the signal not too far away from the center of one of the green regions. You can see overload is blinking here. This is minus 10 dBm. I changed to minus 13 dBm. Like that. With 32 segments, we have 96 divided by 32 kilohertz per segment. That is 3 kilohertz. So I set the generator frequency increment set to 3 kilohertz. And now I can start to step. And on the high side, on the screen high, in frequency actually low. And the points have to change from magenta to green. And they all have changed now, except for points out here and out here. So the next step is you compute the new calibration function. U. And to look at it, I press minus. And you can see, given the segment size 32 over the screen, we can see that from here to here is about one segment. So 32 segments is not really enough for this hardware. But to show what result we got, I will accept it, press enter, and then just S to save, and X to come here and back to the processing screen. And look at the result. The signal is at about 130. The mirror is at about, what can it be? 75. So that is 65 dB. That is the ends of the spectrum where balancing is worst. So I go further into, and you can see when we are 10 kilohertz from the end, we have 130 and 50. That is 80 dB. That is more or less good enough. And it becomes a little bit better towards the center. And on the other side, you can see it goes up. And here it is only about 40 dB mirror image reaction at the end of the passband. This is because 32 points is not enough for the WSE system, which has very steep filters in this frequency range, which means that the phase changes rapidly with frequency. So now I repeat the calibration, X, C, and A. And now the frequency range is split in 32 segments. I change that to by plus 64, 128. And I have to go to the center to look at how the signal is placed with respect to the center frequency. And to see better, I removed the old calibration function. That is C for clear the RAM. And there we are. And now the segments are 750 Hertz. Something like that. Now the signal here is well separated from the image there. I clear again. You can see that, hopefully. And clear. Now the signal and the mirror are both within the same segment. They are both green points now, as they should be. I think I should be even a little bit further close. Something like that. I can verify that this works by computing the mirror rejection just from one segment. That is U. And you see it now is flat. It will apply the same over the whole frequency range. Enter. And we can see here the amplitude of the mirror image is 0 and 3 zeros 3. And you can see it varies a lot. It's down in the noise. We have the sideband noise from the generator. We can do better than this by increasing the number of points in the FFT. That will, on the other hand, make the process a little bit slower. So this should be good for calibration. I have to change the step size to 0.75 kilohertz. 0.75 kilohertz. And then just step. And you can see the unbalance is about 1%, a little bit less. And that is about 40 dB. It's an amplitude ratio. And I stop the filming here and come back when it's finished. At the passband edge, the signal might become too weak. It's now minus 13 dBm. I go up a little bit to minus 5 dBm, say. And then we get that point as well. And now compute new calibration and store it in RAM. That's U as usual. And have a look at it. I press minus so we can see. And you can see we have now smooth shapes here. Probably to get this region accurately described, one would have to have even more segments. But it's not worth it. It's in the passband edge, and our interesting signals shouldn't be there anyway. We don't want... we should avoid very strong signals near the passband edges if we want to listen to weak signals at the other passband edge. That's a limitation, and if you want to spend a lot of time on the calibration, you can avoid this problem, but it will require good temperature stability on the unit, because these are consequences of very sharp filters. So enter, save, exit X, and then back B. And have a look at the result. I make the frequency step 5 kilohertz and step the frequency. Now at the end of the spectrum we are here at 70 versus 130. That's about 70 dB. And a little bit closer, then we have better. It's 50 and 130. That's 80 dB, this level. And then it becomes better over the dominating range of frequencies. And at the other end of the spectrum, we get a strong signal again. Well, strong and strong. It's now 130 minus 65. So that is 55 dB image rejection at the edge here. I think this is perfectly okay. Now I have replaced the signal generator with the pulse generator. This thing contains a 555, which frequency can be set by the knob and the two switches. It's followed by a divide by 2 IC 74 AC 74, and then a 6 inverter IC. That's a 74 ACT 04 with all 6 gates connected in parallel. An RC link at the output makes a high-pass filter, so the pulses have a length of about 10 nanoseconds and an amplitude of about 5 volts. Like before, the signal enters the WSE units through a 3 dB hybrid into the 10.7 MHz input. It is not suitable to calibrate on the 2.5 MHz input, because at that point the frequency response is sensitive to the input impedance. But it's okay to calibrate on 10.7 or on the HF inputs, or also on the 2 meter input. It doesn't matter. The selectivity, all the selectivity comes from the 2.5 MHz to audio converter. The pulse amplitude is 5 volts. That could be a little bit too much. I don't remember. When doing this, it's a long time since I was playing with the WSE units before. So I make a test here. Look at this S meter. And I expand the scale to see well. Like that. And I want to look at the RMS power. here. Now I introduce, now I introduce 10 dB attenuation. And it looks like we got 10 dB less signal. So for that reason it should be safe. We are well below where anything saturates. So to calibrate the frequency response, X, calibrate, B. The repetition frequency is fairly high. I make it lower. Now it's 95 Hertz. You can see the frequency response is rather complicated with several lobes here. It's because of the sharp filters, the anti-alias filters. So let's try enter. And now Linrad is collecting the average of the amplitude, that's magenta, and the average of the second derivative of the phase, and that is green. And I wait for a while to allow very good statistics. Now it is nearly 5,000 pulses. That is more or less overkill. And here you can see the yellow is the correction we will have to apply. At the edges the gain was a little bit higher, so the calibration function will reduce the gain at the edges. Accept the default by Y, and here is the result, very flat. Save this as S, and then exit X and back B. And here you can now see a very flat frequency response. How flat it is can be inspected by allowing some expansion of the frequency scale. And the repetition frequency is only 100 Hertz and it's only 9 averages. I make the averaging bigger, 200 maybe. And it looks very flat. Now I increase the signal level by 10 dB. This is to verify that the shape didn't change. And you can see actually it did. It now slopes just a little bit from here to here. I can expand the dB scale a little bit extra. We have a slope of about 0.2 dB, and that is with 5 volts amplitude on the incoming pulses. So attenuate by 10 dB again here. And we have to go up by 10 dB here. And here you can see it is flat. I attenuate 10 more dB. It is 40.8. So it should be at about 30.8 now. And I cannot trust the attenuator for the decimals of a dB, but you see it is flat here also. So it was a good idea to use the attenuator for the calibration. And now to show the result, I'm going to enable the second FFT. That's X, P for parameters. Enable, putting 1 here. And that gives a new window with the second FFT. Oops. And I rearrange a little bit because I want to run the TIMF2 second time function oscilloscope, which is only available to experts. That's why I started this video by saying I'm an expert. You don't need it to run, but I need it to demonstrate and to talk about things. And I remove the blanker. That's the smart and that's the dumb blanker. And you can hear the pulses from the pulse generator. Switch on the oscilloscope, that's the O down here. And we have a big pulse. I reduce the gain by clicking the minus box. And here is the peak amplitude. That's the maximum of a single pulse. And enable the smart blanker like that. And you can see the pulses are weaker, but the effect is not good at all. I magnify with a plus, that is 6 dB, 12 dB. The smart blanker does not work well here. The reason is that the frequency response has a big curvature. I have to remove the discontinuity at the center. That is the next step of the calibration function. X, Calibrate, remove center discontinuity, that's C. And I go for defaults, continue. That means that we are fitting polynomials to the Fourier transform of the pulses, but not to the center 500 Hertz of the frequency response, because that's the region where the discontinuity is. Continue, and then I press plus to see better. The yellow curve is the actual measured power function, and it's the symmetrical combination of the power on the high and on the low side of the center. And the red curve is the difference between what is measured and what comes out from a polynomial fit with only 3 terms. And the agreement is almost perfect all the way up to this point. So I can replace all the points at the right side of the blue line will be replaced with what comes from the polynomial fit. So this is fine. A. Here you can see the yellow curve what it really looks like. To see that, I press minus. Is a reasonably straight line. I fit a 5-order polynomial to it and replace the region from the blue line and all the way out with what comes out from that polynomial fit as A. And the same. And once, no, here only 3 terms are fitted, and you can see the red curve goes up and down a little bit. And the discontinuity seems to be only 2 or 3 points out here. So I increase the number of terms, let's say 6, 7, maybe, and use that, A. Now the amplitude function is like this, and the phase versus frequency. And I think this is still the second derivative, but I'm not sure anymore. Anyway, update and save to disk, that is S. And then back to SSB. And we have the blanker running, but there is no pulse anymore. We were, was it 12 dB below, I think? Plus 24, 30, 36, approximately 36 dB. Click on a frequency and make it 10 dB per division. And then switch off the blanker. So it goes from 24 to 56 dB, something like that. And I can now also enable the dump blanker, and not so much, just to remove the strongest pulses here. Maybe something like that. And you see it's 1% or below. The dumb blanker will take care of pulses that are long, that is noise bursts. But it is unsafe to remove long interference sources, long interference pulses, because of the wide bandwidth. If there are other signals, they will be modulated by removing, and that is the typical problem one has with the ordinary kind of noise blankers. I expand the dB scale. And increase the bandwidth a little bit to get a smoother S-meter graph. Make it also a little bit slower. To see small changes of noise better. So I switch off the dumb blanker. And you can see it makes about 1 dB. Switch on the dumb blanker and switch off the smart blanker. And you can see it's equally good. But now we are cutting a big hole here. That is 4% of all the data. With a higher pulse repetition frequency, like this, Now it is the dumb blanker. It removes 9%. We have quite a bit more interference. Add the smart blanker. You can see it makes a difference. You can bring down the threshold for the dumb blanker a little bit. And I want to look at the spectrum, whether there are any red points here, and there are not. I can see here very seldomly there is events, that is strong signals routed outside the blanker. There will be more about the operation of the blanker under real circumstances in other videos.